Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Today we are going to continue working on the shader compilation. As I mentioned in the last video, user-defined shaders are going to be a part of materials which will be used to render a submesh. Therefore we need to be able to compile such shaders on demand. We will start today's video by writing a function that will load a shader file and compile it using the Directx Shader Compiler. We are going to continue where we left off here in shadercompilation.cpp by adding a new function that will take a shader file, compile it, and return a pointer to the compiled shader information. If we look at this compile shaders function, which we wrote to compile the built-in shaders, we are creating one shader compiler instance and use it to compile multiple shaders. In contrast, in the current function, we instantiate one shader compiler each time we want to compile a shader. I did a tiny bit of research about the cost of spawning DXC instances, and according to this developer, who is one of the DXC's contributors, it's not that high. After creating a compiler instance, we can use it to compile the shader. If compilation was successful and we got a valid pointer to the bytecode, we can allocate a buffer and pack the information in there. In order to do so, we first need to decide what format we are going to use to pack this buffer. We already have something that we are using for the built-in shaders. Let's move that to content to engine header and expand it to contain the hash code. Here I also add a constant for the number of bytes in the hash code, which is 16 as you can see here. Please keep in mind that this structure merely defines the format of our buffer and it will not contain the full bytecode. You can view this as a rather elaborate pointer type. To make it easier to work with this type, I'll add an accessor function for each of the member fields. Let's move primitive topology to renderer.h because it's more related to graphics than it is to content. Because we added this structure to content to engine header, we need to include this header in order to use it. We need to do that here in the 3D12 shaders.cpp and also update the function that loads the engine shaders. Instead of accessing the fields directly, we can make use of the accessors. I also fixed the typo here. Now we can continue with our compile shader function. After including the header file, we can make sure that our constant for hash length is the same as the one used by DXC. Next, we calculate the size of the buffer that we need for packing the information and allocate a buffer with that size. Now we can use our trusted blob stream writer to write the shader data to this buffer. At the end, we return the unique pointer that points to the buffer. If compiling the shader failed, we return a null pointer. Because we moved primitive topology, we also need to update how we refer to it. As you can see, it makes the code simpler and shorter, which makes me think that it was a good decision to move it. Here is another typo from the last video. And in order to be able to use a U32 type, we need to include the common headers file here as well. We also need to use a 64-bit unsigned integer for buffer size here, or we could typecast the return value from getBufferSize. Now that we managed to successfully build the engine, we can try and test if we also can compile shaders from any file that we would like to use for user-defined shader code. Therefore, I'm going to add an HLSL file where we can write a vertex shader and a pixel shader, which we'll use to define a material for our render item. To do this, I'll just copy one of our existing shader files and write our shaders in here. First, I'll quickly define our global data type that will be accessible to all shaders. It contains things like view and projection matrices and camera position, view dimensions, and frame time. While we are at it, we can also define a per-object data type that contains the transform matrices for each object. Next, we'll define an output format for the vertex shader. There could be more output formats depending on the vertex type that the object is using, but this one is a rather common format. We can also define the pixel shader output type, which for now is just a color. Next, we can write the vertex shader and pixel shader functions. Because we are not rendering anything yet, I'll leave these pretty much empty. They are, however, perfectly valid shaders that we can try to compile. In the render item.cpp, where we were writing this load shaders function, We are going to initialize shader file info with the file name of our shaders and the function name for each shader. We need to add the function declaration for compile shader that we just wrote so that we can call it. In the load shader function, we call it once for the vertex shader and once for the pixel shader. Obviously, if you'd like to keep these shaders around for rendering, we need to pass them to the engine. So let's write a couple of functions that we can call to add and remove shaders. I also add a function which we can use to get a pointer to the compiled shaders. We put all these functions in content to engine module. Here we can have a free list for compiled shader functions. In addition, we need to use a mutex because shaders can be loaded using multiple threads. Note that although we are compiling shaders for our Direct3D renderer, we are keeping the bytecode in an API-independent part of the engine. This is because a block of memory in and of itself is not related to any API, and we could use the same code path for any other binary shader format. If in the future this turns out to be a poor design decision, we can always move this part to the low-level renderer and use the graphics interface function pointers to add and remove shaders. In the add shader function, we allocate a buffer and copy over the shader data. Then we add a pointer to that buffer to the free list of shader pointers. In remove shader function, we simply remove the pointer from the free list, which automatically also frees the allocated block of memory. Finally, the getShader function returns the compiled shader pointer at the provided index in the free list. Now let's add the compiled vertex and pixel shaders for our test application to the engine. Before running the application, we need to recompile the built-in shaders because we changed the data format to which they are saved. We can trigger a recompilation by removing the shaders folder. We have an error during this compilation, so let's see what's causing it. We can see the error message in the output panel, which tells us that there was a compiler option that wasn't recognized by DXC. Looking at the code where we provide the arguments, I see I forgot a comma for this new option I added in the previous video. Adding the comma should solve the problem. Running the application again, this time we get an exception when we try to create a pipeline state. The error message lets us know that we are using a shader model that's not supported on this machine. Note that we successfully compiled all our shaders using shader model 6.6. However, these shaders can't be used on a system that doesn't support this shader model. I know that my graphics card does support shader model 6.6 because it's a fairly new RTX card. I also have the latest drivers and Windows updates, so I'm not sure why we get this error. maybe we need Windows 11 in order to have support for later shader models out of the box. Fortunately, there is a way to enable this shader model and the latest Direct3D features for any graphics card that supports those features, and that's by installing the Direct3D 12 Agility SDK. It's a couple of DLLs packed in a NuGet package, which when installed will replace the Windows DLLs if those DLLs are older than the ones that come with the NuGet package. So to install it, we can open the NuGet manager and search for Agility SDK, and as we see here, the latest release version is available for download. We only have to install it for the engine project. On this page you can read all about the mechanism that's used for loading the right DLLs. You can find the link to this site in the video description. Here is the section about how to use the SDK, which also has detailed information on how to set some of the parameters to better fit the developer's need. We can skip most of it since we are not special needs developers. However, in order to let the runtime know which DLL should be used, we need to add these 2 lines of code to our engine. So let's copy the lines and paste them in D3D12 core.cpp. This basically exports 2 symbols for the runtime to be able to check which SDK version we are using and where it can find the corresponding DLLs. Here we need to use the SDK version instead of N. We need to use the minor version number here, which is 606. And that's all we need to do to use the Agility SDK. To summarize, step 1 is to install the NuGet package, and step 2 is to copy these 2 lines of code to our engine. Now we can build and run the program. Here we can see that our shaders were compiled successfully, and we can see the resulting hash code as well. However, we also get an error about mismatching barriers. This is an error that's caught by the newer debug layer from the Agility SDK, which is great because it means that it's working as intended. The error is about the fact that we are using split barriers across 2 different calls to execute command lists function. What I really like about D3D12 debug layer, or their error messages in general, is that it exactly states what the error is, instead of just giving some cryptic error message like we get from C++ compilers. Here it says that splitting barriers across calls to execute command lists is not supported, and it also has no benefits since everything is already synchronized. We can also see that it's our GPass depth buffer that has the mismatching barriers. Good thing we named our D3D objects, right? Okay, let's head over to the GPass module and fix the problem. Here we see that I'm indeed using a begin-only barrier at the end of GPass, and in the next frame I'm using the end-only barrier. To fix this, we can simply remove these lines and get rid of the flags variable as well. Now the depth buffer is transitioned into writable state just before the depth prepass. I'll remove all references to flags and we can try running the program again. This time we succeeded, but the resources that are created with the render item are not released, which triggers some assertions. We can fix that by implementing destroy render item function. Let's pretend we have a valid item ID by returning 0. Then we can check if the item ID is valid, and if so, remove the game entity and the render item. I'll do that in a second, but first let's unload the shaders and the geometry resource. So we check if all IDs are valid, and then we remove each resource. Next, I'm going to map each render item to the corresponding entity, because we might want to create more render items later on. We still need to write the code that actually creates a render item in the engine, but for now we can return 0 as an ID. When removing the render item, we look up the entity that owns it and remove it. When we also have the engine function that removes the render item, we'll call it here as well. Now we can run the program without errors and leaks, which is great. So today we finished updating the shader compilation module so that we can compile user-defined shaders. We also added the Direct3D Agility SDK, which grants us access to the latest features as long as those are physically supported by the graphics cards. By doing so, we gained access to the features available in Shader Model 6.6. Before we continue our work on render items, I'll take a little break from this in the next video. As we all know, Visual Studio 2022 has been released for a while now, and I think it's stable enough for me to use it for these videos. So I'd like to spend the next video upgrading to Visual Studio 2022. And last but not least, I need to make a couple of small changes in Primal Solution in order to make it more platform independent and also easier to use together with Primal Plus. I'll tell you a lot more about this in the next video, so stay tuned. As always, thank you for joining me today, and I hope to see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering.